Okay, picking up where we left off in 6.1 yesterday, my plan is to finish these notes, and then in 6.1.2, I'm going to do one example there, and that one example goes with the 2 extra problems that I added and threw some of you off, okay, which they were going to be up here today, and I just didn't get quite as far as I planned yesterday. So I believe this is where your class ended yesterday, if I'm not mistaken. We had talked about the unit vector and verifying its length, and I was getting ready to talk about another way to write component form. Okay, so there are 2 basic unit vectors, I and j, where I is the vector 1, 0, and j is the vector 0, 1. And we can use these unit vectors to basically write component form, to write all different vectors. So for instance, the idea of vector a, b can be split into 2, where it's a, 0 plus 0, b. And think about that. That's just those 2 vectors added together. And then if you kind of factor out the a and factor out the b in a way, then it's a times the unit vector 1, 0 plus b times the unit vector 0, 1. Well, again, 1, 0 is known as I, 0, 1 is known as j. And so another form, besides just writing it like this is our component form up here, another form besides the component form is this form right here, which is referred to as a linear combination. I don't remember exactly how the directions read in homework on various parts, but if you're asked to write something as a linear combination, this a times I plus b times j is the idea of what we're looking for here. So, for example, if I take the unit vector from above that we had above of negative 3 over square root of 13, comma 2 over square root of 13, I can write that as a linear combination because my a component is negative 3 over square root of 13. So I can say negative 3 over square root of 13 times I plus the b component, so 2 over square root of 13 times j. That's an example of a linear combination using the unit vector from above. So those are equivalent forms here. Okay? Just it depends on what they ask, what form they want. So I want you to be a little familiar with that. By using this format, we have a linear-like combination using vectors I and j. The scalars or constants a and b are considered the horizontal and vertical components of vector v. And if you think about it, it's just like an ordered pair in a way. A is our x value, and a is how far you go left or right, so a horizontal component. B is our y value, so how far you go up or down, and thus our vertical component. Before we go into the bottom part here, we're also going to talk about finding direction angle of a vector. The direction angle of a vector is the angle theta that the vector makes with the positive side of the x-axis. Using trigonometry, I told you guys it's not going away, right? And this is where I said have your calculators out today. The horizontal component of a vector, so in order to find a, it's absolute value of v times cosine theta. Remember, absolute value of v is the magnitude times cosine of the direction angle. And then the vertical component, well, vertical component is, for the b is absolute value of v times sine theta. Or in other words, magnitude times sine theta. If you remember our ordered pairs on a unit circle, right? Ordered pairs on a unit circle, x comma y, or cosine comma sine. Same type thing here. We have cosine for the first one, sine for the second one. So a vector written with the horizontal and vertical components. Now there is a slight, very small typo here in that the absolute value should be around the v, not around the v and the cosine. Sorry about that. So it should say absolute one way to write it is absolute value of v cosine theta times I, like that's a way to find A, plus absolute value of v times sine theta times j, because that's a way to find b. You will notice over here the u equals, well, u is often representative of the unit vector, and a unit vector is a vector that has a length of 1, right, or a magnitude of 1. So you'll notice if it's specifically a unit vector, there's nothing in front of the cosine theta and sine theta because the absolute value or the magnitude would be 1, so you wouldn't have to have it in there. And you'll also notice this is in the form, I think I already said it, but A times I plus B times J. So, if you guys are ready, let's look at example 4 and use some of this information I just went over. Example 4 asks us to find the components of the vector v with a direction angle of 115 degrees and a magnitude of 6. So it's asked me to find components, and when it's asked me to find the components, it's basically asked me to find A and B. Direction angle of 115 degrees. What is that direction angle represented by in our formula that we're getting ready to use? Yeah, that's our theta. So direction angle of 115 degrees, so that is going to be theta. And a magnitude of 6. What's magnitude represented by? Okay, the absolute value, right? So this is the absolute value of the vector. So we have formulas that we can use to find A and B, correct? If you go back to what's right above it, A is our horizontal component. A is the magnitude of the vector times cosine theta. Can you fill in the information? We're trying to find A. In place of absolute value of V, we're going to fill in 6. Cosine of theta, what am I filling in for theta? 115 degrees. Let the calculators do the rest of the work. Give me a calculator answer.
I got a negative 2.5.
I have written down negative 2.54. So sounds like you are on the right track. So that is our horizontal component of A. If you did not get that, double check your calculator. You should be in degrees. We haven't been out of degrees lately, but trying to think what other, make sure you're getting the right things on the calculator. Can we also find B? A was easy enough, right? B is just the same except using sine. So absolute value of V times sine of theta. So for absolute value of V, again, you're filling in 6 times sine of 115 degrees. Okay, did you check your calculator? Do we agree? If you've already done it, that is. 5.44. Now, it specifically just says find the components, so as in find A and B. I am going to show you, depending on what they ask, component form. Realizing one way we can write component form is just the A comma B with the vector pieces, right? And so one way to write this answer in component form would be negative 2.54, comma 5.44. Again, depends on what they ask for in homework. The other way would be to write this as a linear combination. So A times I plus B times J can be written as a linear combination. And so in this case, I would write it as negative 2.54 times I plus 5.44 times J. Just variations of how you can write component form. Questions there? Depends what the directions of the problem say. I honestly can't say that I've looked at the homework this morning to remember, but I do feel like it might ask for both. Don't quote me on that, though. I'm just kind of trying to express that they are both component form. I'm ready for example 5 when you are. Example 5, there is an A example and a B example, yes. And it asks us to find the magnitude and the direction angle of each vector. Okay, well, I would like to think you guys know how to find magnitude. What are we finding? We're finding magnitude. Yeah, that's that absolute value, isn't it? Whoops. I guess they called this one U. So absolute value of U. So how do we find that? It's already in component form, so remember you're doing okay. Square root of first component squared plus second component squared, so square root of 3 squared plus 2 squared. 3 squared is 9, 2 squared is 4, so this is going to be square root of 13. And that is your magnitude. We're also being asked to find the direction angle of each vector. So direction, if we're being asked to find the direction angle of the vector, we're being asked to find theta. What do we have in it that uses theta? We just have something in it above that uses theta? Yeah, we have those, the information to find A, the horizontal component, and B, the vertical component, yes? So, okay, look at what you're given. We were provided the vector 3, 2. And that vector is in, if you will, A, B form. Because A is the horizontal component, B is the vertical component. So with that in mind, a vector could also be written as magnitude of U times cosine theta, and magnitude of U times sine theta. So the idea that this 3 right here is going to be equal to the magnitude of the vector times cosine theta, and this 2 over here is going to be equal to magnitude of the vector times sine theta. Can you set up an equation? technically we could set up two equations. And you can pick which equation you want to set up. Okay? Doesn't really matter either way. So if I use my horizontal component, my A, then I know that magnitude, what's my magnitude? Square root of 13 times cosine of theta is going to equal 3. Or, if you prefer, you can say square root of 13. What did I just do there? Square root of 13 times sine theta equals 2. Does it matter what you use? Okay, so the idea, we were given the vector 3, 2. So we have the horizontal component and the vertical component. If you go right up above here, we talked about that the horizontal component, so the A value, can be found by doing the magnitude times cosine. And the B value can be found by doing magnitude times sine. Okay? So, you're welcome. All I did was set these equal, and I filled in my magnitude, so square root of 13 times cosine has to be equal to 3, or square root of 13 times sine has to be equal to 2. How do I solve for theta here in the cosine theta one?
Divide the square root of 13 over and then 2.
Okay. So first job is to get cosine of theta by itself. So divide square root of 13. So it's 3 divided by square root of 13. I'm going to work these side by side this time. Next time I'll probably just work one. The other option, if you're saying, nope, I'd rather use sine. Okay, well, how do you get sine theta by itself? Divide the square root of 13 over, so it's 2 over square root of 13. How do I find theta in these when I have cosine theta equals a number value? Inverse. Okay, the little negative 1 thing. Remember, if you're trying to find theta and that's inside your trig function, you have to use the inverse function. So you can say, not what I want to write there. Try that again. Theta is equal to cosine inverse of 3 over square root of 13, and you can go that route. Or you can go the route of theta is equal to sine inverse of 2 over the square root of 13. On this problem, you should get the same answer. Try it. Check your calculator. Make sure you know what you're doing on the calculator.
33.7.
I have 33.69 written down. Did you guys get it? And it doesn't matter which one you do, does it? Now, one thing to consider here, okay? We can do either route. Either route got us the same answer. We always need to make sure that our answer makes sense for the angle. In terms of, do we get the right quadrant for our answer? So go back to me with me. The original vector, 3, 2. What quadrant does that put us in? You go right 3, up 2. That puts us in quadrant 1, correct? What about 33.69 degrees? Quadrant 1? Does it match? Yeah. Okay, so we're good here. 33.69 degrees, legitimate answer. They both came up the same. We're good. But you always want to check that. Okay. Questions? Go ahead, yeah.
The direction angle, it's like the angle that it makes with the axis, or like with the, the origin.
With the x-axis.
Okay.
Okay, let's look at v. V is the vector, -2, -5. We need magnitude and direction angle. How do I find my magnitude?
Absolute value.
Absolute value. So we're going to be doing the absolute value of v. So the square root of
Plus -5.
okay, square root of -2 squared plus -5 squared. -2 squared is 4. -5 squared is 25. 4 and 25 is going to make this square root of 29. Okay, what about theta? We were given v as -2, -5, correct? We know in a vector, the horizontal component is the magnitude of the vector times cosine of theta. The vertical component is the magnitude of the vector times sine theta. Take your pick. What do you want to set up? Technically, doesn't matter.
Sine.
Okay, Abby wants to set up sine. I'll be honest, I was going to go cosine.
I went cosine.
Carly went cosine. In the end, we'll work it out so that we end up with the same answer. Okay? If I go cosine for my main work, we'll talk about sine, don't worry. So regardless, either way, magnitude you're doing square root of 29 times cosine theta equals -2. Get cosine theta by itself, right? So divide by square root of 29, so -2 divided by square root of 29. And then if it's cosine theta and I want to find theta, I'm going to do cosine inverse of -2 over square root of 29. If you went the cosine route, you got 111.80 degrees. Anyone go the sine route?
I did, but I didn't know my answer. -68.20.
So, I'm getting there. Okay, if you went the sine route, okay, and here's the deal. Do you have to work both of these? No, you don't. I'm just, I need to talk about them, though. Whoops. If you went the sine route, you ended up with -68.2. Well, A, we don't have the same answer, so that's an issue. But also, we haven't talked about what quadrant we're in. So, let's go back and talk about our quadrants. -2, -5. Left 2, down 5. We should be in quadrant 3. What range can you expect your answer to be if our answer should be in quadrant 3? A quadrant 3 angle is somewhere between 180 degrees to 270 degrees. Well, this is where we have to talk about is how these are correct in terms of getting us there, but in order to, let me draw a picture, okay? Let me draw a picture to try and explain what we're looking at here. So if we look at cosine for a moment, sines, hold on, we'll talk about you in a moment, okay? If we look at cosine, 111.8 degrees. Well, trying to think, where should it be? About in there? Past 90, before 180. I probably went a little bit too far, but that's where the angle ends up. That's where 111.80 is, yes? However, okay, here's the reason why it's doing that. Cosine inverse, if you remember our inverse, cosine inverse will give me an answer in quadrant 1 or 2. Does that sound familiar? Because sine inverse will only give me an answer in quadrants 1 or 4. Cosine inverse will only give me answers in 1 and 2, between 0 and 180, right? So we have to adjust it to make it work. Now, this is 111.8 degrees going in the positive direction. Well, what you're looking at is, what do I use here, red? How far is this from the x-axis? Except we want to be down here in quadrant 3, so we're going to say, how far down is that? Am I making sense here? So this is, because it's just like reference angles. It's how far it's in relation to the x-axis, right? So we went 111.8 degrees this way, and we ended up over here, but we really need the equivalent down in quadrant 3. I also think of it as, how do I get there? Okay, there's a couple ways you could do the math. What math can I do to get to this angle?
180 minus. Well, you do. Oh wait, yeah, you're right. Just keep 180 minus 111.
No.
No. 180 minus. But don't use 68. You add together. 360 minus.
Okay. One option, which is the way my brain goes, again, not the only right way, is that if this is 360 right here, could we go 111 from the 360? And so in other words, you're doing 360 minus 111.8, and you end up with what? $248.2. Okay. Now, I know you girls were wanting to go off of 180. Well, here's the deal. If this is 111 over here, you're going to have to figure out, okay, 180 to 111 is how far, and then take that distance and add to 180 down here. Okay? Now, let's think about this one. Negative 68.2. Well, negative 68.2 is going where? It's going down there, yes? Because again, we're in the assigned quadrant, only give me answers in quadrants 1 and 4. Negative 68.2 is down here. What do we need to know? We need to know, okay, we need the equivalent angle down here. So if you got that 68.2, you can look at the fact of, what's the math I could do there? I think someone started to say it earlier for the other one. But if this is going below the axis, this is 180 right here, yes? And that's the thing you have to keep in mind. That's 180. That's 360. So you could take 180 and, not minus, because you're going past 180, so you're going to add the 68.2. And guess what 180 plus 68.2 is? 248.2. Okay. So the catch there is you have to make sure you land in the right quadrant, and it has to do with using the inverse trig functions. Because inverse sine will only put us in quadrant 1 and 4. Inverse cosine will only put us in quadrant 1 or 2. Well, this is the catch one, right? It's in quadrant 3. So you have to think through it. Okay? Now, this is what I planned to finish yesterday. And then, or get more through than what I did. I want to go to the next page, 6.1.2. We're going to do one problem. And that's all my plan is for 6.1.2. So we're going to do example 1. And I believe, if I haven't made a mistake, that's what goes with 41 and 42. Okay? So, some applications of vectors is what this section looks at. And again, for those of you that end up seeing physics next year, you know, this will definitely be familiar stuff, okay? On years when their physics is going the same time, this is definitely, you know, familiar stuff with them. But velocity. When we talk velocity, we're talking kind of like speed, right? Like miles per hour, meters per second, those type of things. The velocity of a moving object is a vector because velocity has both magnitude and direction. Now, magnitude of velocity is speed. So keep that in mind, that magnitude of velocity is speed. And then it also talks about force as a vector's magnitude, which the force example is example 3, and we're not doing the force example. Okay, it's more than I want to get into. So let's look at example 1 here and see what we can figure out. A DC-10 jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. Note, the bearing of the airplane is the angle that the line of travel makes with due north measured clockwise. You have to watch out for that word bearing, because right now we are all trained that where is 0? 0 is at 3 o'clock, yes? But when they throw in the word bearing, 0 is now north, is what we're going with. And you're going clockwise from there. So you have to be very careful here. Let's go for a picture. It's a word problem, right? What else would Mrs. Sargent do besides a picture? I'm drawing in my x-axis and y-axis, because that's what I'm really working on here. Keep in mind, though, my y-axis is north, isn't it? So a jet aircraft is flying on a bearing of 65 degrees. How do I measure that 65 degrees? Notice it says the bearing of the airplane is the angle that the line of travel makes with due north. So where's my bearing of 65 degrees going to be? From 0, we're going to go right 65 degrees. So the idea of right 65 degrees is going to end us, it's not exactly right, but something like that. I really don't like that picture, but oh well. With that in mind, okay, this is essentially our vector that represents a jet, and it is flying at a speed of 500 miles per hour. What do we know about that 500 miles per hour?
The magnitude.
It's magnitude, right? In terms of vector terminology, our magnitude is 500 miles per hour. And that's because magnitude of velocity is speed. And so when we think in terms of the equation that we're going to set up, essentially we're talking about the absolute value, I'm just using V. Since magnitude is 500, the absolute value of V is going to be 500. Okay. I also need a direction angle. Thoughts about my direction angle? Yeah, 90 minus 65, because here's the deal, guys. Your direction angle is based off of the x-axis. Is 65 degrees off of the x-axis? It is not. It is doing 90 minus 65, which is 25. So the other piece of information, in order to do this problem, we need the direction angle. And in order to do that, 90 degrees minus 65 degrees, which is 25 degrees. Okay. It asked us to find what? The component form. Yes? Well, in order to find component form here, we've got magnitude and we've got an angle. So we can go back and use that idea of magnitude times cosine theta and magnitude times sine theta. Well, fill in what you know. Magnitude is going to be 500 times cosine of 25 degrees. That's for my horizontal component, or component A. And then over here, magnitude of 500 times sine of 25 degrees. And that's going to be for my vertical component, or component B. This being A, this being B. I didn't write it like I normally write it, but. Okay, did you do the math? $500 times cosine of 25 degrees should be
453.15.
453.15. Vertical component, 500 times sine of 25 degrees.
211.3.
211.31. Okay. That is our component form. A little bit of extra information to tag on. I keep mentioning this is the A is the horizontal component, right? And B is the vertical component. So a little bit of connection here. If this is horizontal and this is vertical, well, what we're looking at here is these are both miles per hour. And when we talk about that, the horizontal direction, well, horizontal, that's like going east and west. And if we're going to the right, that is going to be an eastward. That's going to be your speed as you're going east. And 211.31, that's your vertical component. Well, north-south, but this one is a north. So this is a northward. So a little bit about what this vector represents is that this plane is going on 453 miles per hour in an easterly direction and 211 miles per hour in a northerly direction. Maybe I should have used easterly and northerly. Okay, if you have not already written down the homework, make sure you do that. Make sure you add the two problems that I added in. They had not put up yesterday. So page 464, numbers 5 through 8, 13 through 20, 25 to 34, and 41 and 42. Finish this homework for tomorrow. I'm ready to check it and go over questions.